we now come to the topic of waves. And the first couple lectures here are going to give more or less some of the mathematical background um, and descriptions before talking about some of the nuances in depth, right? So, first things first, a wave is a propagation of energy, okay? That's one of the basic definitions. Now, what we're going to focus on are what are called mechanical waves. And mechanical waves require a medium for the energy to propagate through, okay? So, some examples of mechanical waves. The first would be sound. And the medium for sound is typically going to be air. But of course, sound can travel through water, it can travel through different solids and things like that. But it has to have some sort of medium to travel through, right? Another one would be a water wave. And when, like, if you make a splash in a swimming pool, for example, right? What happens is you create a disturbance on the surface of the water, and then that disturbance propagates through the water. So if you've ever made a splash or thrown a rock in, and you can actually see the waves traveling away from the initial point of disturbance, then that is this principle in action, for example. Earthquakes. And the medium here is actually the Earth itself. And the waves can actually either propagate along the surface or through the interior. Okay. Now, an example of a very important wave that's not a mechanical wave is light. So, light does not require a medium. And this actually has some very deep implications, as you'll discover if you take 299 and beyond. But it does transfer energy. Okay, light is a transfer of energy or a propagation of energy. Okay, and lastly, there's also the issue of particle waves. So, if you've ever read anything about quantum mechanics and heard about the wave particle duality, that's where this comes from, uh, where subatomic particles have wave properties. So for this course, we are going to focus on mechanical waves. Okay, so we'll save the discussions of light and particle waves for future courses. But they share a lot of the same mathematics, which is actually kind of interesting. Okay. Now, we typically think of a wave, you know, if you think of throwing a rock in a pond, and you actually see the water waves move through the water, right? You'll notice they actually look somewhat sinusoidal. Okay, and y is the displacement of the water, and x is the propagation of the water. All right. And it turns out when you have a wave that it actually travels and looks like this, this is what we call a transverse wave. So if the wave is traveling with some velocity in this direction, then its amplitude or the displacement, the amplitude is the maximum displacement. Both of these are amplitudes. Okay. When your amplitude is perpendicular to the direction of your propagation, so the wave is, if this is the original source of the displacement, then the wave is traveling to the right, but the water itself is bouncing up and down. Okay. So the direction of propagation is perpendicular to the disturbance direction. All right, so your water is bobbing up and down, but the wave itself is moving to the right. Okay. Contrasting with that, we also have what are called longitudinal wave. Okay, so a longitudinal wave you can think of like a slinky that you stretch out and then scrunch up some of the coils on one end, and then you let it go. Okay, so this is at t equals 0, and what you find is as the tension in the coils pulls this compression, the tension from the stretched coils will pull that compression this way, and an instant later that compression will be in the middle of the spring, and then it'll be stretched out again. Okay, so what happens is the velocity now is actually in the direction of the compressions. Okay, so longitudinal waves are when the propagation, the direction of propagation is parallel to the disturbance. Okay, so examples of transverse waves include water, strings on, taut strings. Okay, so it can be like a guitar, plucked strings, I really should say. Light is also a transverse wave, even though it is not a mechanical wave. Light is also transverse. The biggest example of a longitudinal wave, once you get past the slinkies and springs and things, is sound. Okay, so sound is a compression wave. of the air molecules. And when you disturb those air molecules, they bump into each other. And then that disturbance spreads out throughout the medium, throughout the air typically. But it's literally these molecules and atoms in the air, assuming you're in air, are doing exactly what this slinky is doing. That disturbance is moving through the slinky, and when it hits this boundary over here, the wave will get reflected, and this disturbance will just keep bouncing back and forth between the two endpoints. Okay, and that's what sound does. Your molecules just keep bumping into each other in the direction of their propagation, and that's what causes the sound waves to spread out. Okay. So transverse waves, when you actually bob up and down while you're moving forward, and longitudinal waves you can think of as compression waves. All right. So, how to describe a wave mathematically? The way to describe a wave mathematically is if we look at a wave, a regular sound wave, not a sound wave, I really shouldn't say, but maybe a water wave. Okay, and you actually can see this shape. Okay, there's actually two things that are happening. All right, if I look at the x-axis, then I can actually see this disturbance traveling with some velocity v, and that will just be dictated by the time it takes for, say, this crest to be repeated and come up over here. Okay, so whatever this distance is between these 2 points, for example, my velocity is going to be the distance between those 2 points. The displacement between those 2 points divided by the time it takes for one crest to then go through one cycle to the next crest. Okay, so there's a quantity associated with waves that we call the wavelength. And that is the distance between two same points on the same cycle. Okay? So your wavelength, colloquially, you can think about your wavelength as the distance between crests. But formally, it's the distance between any two similar points on the wave. So for example, if I look at this point here, I notice that this is where the wave crosses the x-axis, or the y equals 0 point rather, and the wave is traveling up this direction. So if I trace this wave to the same situation where the wave crosses the y equals 0 point and then is also traveling in the upward direction, this is also a wavelength. And you'll notice that those two values are always going to be the same for the same wave. Okay? But remember, the time it takes for the wave to complete one cycle is the period. So, if my displacement happens to be one full wavelength, that means that it took one period, capital T, to move between those 2 points. So the velocity of my wave is also my wavelength divided by my period. But my period is the reciprocal of my frequency. So here's a fundamental relationship. Okay? The speed of a wave is equal to its wavelength times its frequency. Okay? The speed of a wave is equal to its wavelength times its frequency. But if we kind of go back to the idea of circular motion that we introduced for oscillations, okay, then we define two quantities, one of which we've already defined, which is the angular frequency, which is 2 pi times f. Then we also define a quantity called the wave number. We call it K. Which is equal to 2 pi over lambda. And we'll see why this is the case. Okay? We'll see why this is the case here shortly. But keep these two quantities in your back pocket, and therefore in these terms, my velocity is also equal to omega over k. Okay? So these two expressions are equivalent, all right? My velocity is equal either to my wavelength times my frequency or my angular frequency over my wave number, right? Okay, so how do we describe a typical wave? And let's actually make this in black. So again, the simplest wave is this sine wave. However, let me come back here. So you'll notice that if I just watch this wave in time, okay, then each point on the wave is just going to be bouncing up and down. Okay, each individual point on the water just bounces up and down. And if you want to prove this to yourself, throw a beach ball in the water. And yes, it is true that you can push the beach ball to the edge of the pool by creating waves and letting it follow the waves. But the bulk of its motion isn't forward. The beach ball tends to just bounce up and down with the water that it's sitting on. It's actually quite difficult to get it to move forward compared to how easy it is to get it to bounce up and down. It does receive a little bit of momentum due to the shape sitting in the water. Some of the push does get moved forward, but it will just typically bounce up and down much more easily than it moves forward. So each individual piece of the water is not moving forward, it's just bouncing up and down. Okay? But the wave itself is moving forward. So a typical wave is a function of both time and distance or position. And so generically, when I have a function of x and t, if it satisfies the condition that it explicitly is of the form you double check that. No, it's omega t. I thought it was omega, but I drew v. Okay. So what this is telling you is that if I have some function of this form, okay, my wave number times my position and my angular frequency times time, under these conditions that they can either be additive or subtracting one another, then these represent a disturbance of both space and time. And you'll notice, okay, this is why k has to be 2 pi over lambda, or at least something where lambda is in the denominator, because your wave number gets multiplied by your position variable. So then kx has to be 2 pi lambda over x, and this is unitless. And omega t is 2 pi over t over your period times t. And so this is also unitless. Okay, so you need your arguments of your wave functions to be unitless, and this lends itself to the description that the simplest wave is a sine wave. Okay, now what this means is if I have a wave and it is traveling to the right, and this is in the plus x direction, okay, then this wave is going to be described by the minus sign in this function. And the reason for this is, think of a quadratic formula, right? If I have x, f of x is equal to x squared, and then I compare that to x minus a quantity squared, this shifts the function to the right a units, right? So when I take the minus sign, what this is saying is when I take the minus sign here, this is saying that I have some base argument, and then I'm going to shift it to the right X number of units, but that number of units is time dependent. So every point in time, the wave keeps moving to the right. So this is a little interesting because, kind of going back to what I just said a few moments ago, the individual points on the wave, the individual points within the medium are oscillating back and forth. They're not moving forward, but the wave itself is. Okay? And so then, if the wave, I'm going to draw it like this, but if the wave is traveling back to the left, then this would be the plus sign. Whoop. Okay. Now, what is the entire business that, these quantities kx and omega t need to be unitless? Well, because the base descriptor of a wave is the sine function. Okay, this is your most basic wave, and the arguments of trig functions need to be unitless, and hence this the argument here will need to be unitless. So A is your amplitude, and then the argument will contain your x's and t's, the variables that actually cause the wave to propagate. So with that in mind, the basic wave can be described as your amplitude times sine of kx minus omega t And if you start your stopwatch at somewhere other than the origin, you can have a phase shift. But your wave could be traveling to the right or to the left, so we'll put a minus and a plus sign there. And then if you start your stopwatch at any time other than when the wave is at the origin, you can have a phase shift, and we will have that. But, okay, so the entire idea of a sine wave from trigonometry is that this is in radians, which is why, which is why k needs to be 2 pi rad over lambda, so that way when it's multiplied by whatever position you're trying to measure the wave at, the meters on your wavelength and your x position cancel out and you're left with radians. And same thing with omega and time, right? So omega is 2 pi rad over your period in seconds multiplied by t in seconds, and your seconds cancel out and you're left with radians. So theta is equal to kx, and whether it's moving to the right or to the left, plus or minus omega t, plus whatever your offset is. Okay. And so this is the wave that we are going to focus the most on. All right. This is the wave that we are going to focus the most on. But this can also be written as Or, let me actually make this minus and plus a little bit more explicit. Or okay. And at this point, all right, if you have a wave of this form, then you can immediately state what the speed of the wave is, right? Because if you know k, then you can calculate lambda, and if you know your frequency, then you can simply calculate the speed of the wave as lambda times f. Or if you're in this form, your speed equals omega over k. All right. So if you need to calculate the speed of a wave, this is the simplest way to do it. So, for example, let's suppose we have a wave okay? So we have a wave that looks like this, and we want to find the amplitude, we want to find the wave number and the angular frequency, and then find the speed of the wave. All right. And so part A is very simple. Okay. The amplitude can be read right off as the leading coefficient. Okay. So if I were to plot this, then this would be the maximum deviation from the equilibrium line, or from the x equals 0. I'm sorry, the y equals 0 line. Okay. Away from the x-axis, in other words. B, well, we compare this with this form. Okay, so that means that k has to equal 0.1, and this is going to be radians per meter, or inverse meters. And omega can be read right off. It is 100, and it will have units of inverse seconds, or radians per second. Okay. And maybe really should write those radians in there. Okay. And then C, what is the speed of the wave? Well, let's do this two ways. So V is equal to omega over K, which is going to be 100 radians per second divided by 0.1 radians per meter. So first of all, the answer is 1,000, but radians per second divided by radians per meter is the same thing as radians per second times meters per radian. And my radians cancel out, and I'm left with meters per second. So that's why this is a speed. Okay. Also, we could do this another way. We could find what lambda is. Lambda is equal to 2 pi over k, which is 2 pi over 0.1. And this is meters. And we can also find the frequency. F is equal to 2 pi over omega. No, omega over 2 pi, sorry. And so this is going to be equal to 100 divided by 2 pi. And then our velocity is equal to lambda times f. And this is 2 pi over 0.1 meters times 100 over 2 pi. And frequency is in hertz or per second. And you can see our 2 pi's cancel out, and I still get 100 divided by 0.1, which is 1,000 meters per second. So it doesn't matter if you use omega over k or lambda f to find the velocity of the wave. You can do it either way. Okay, so this is your introduction to waves. In the next video, we will look at stretched waves on a string and the wave equation, and as well as the idea of resonance. Okay, we will see you then.